طيب, Bismillah ar-Rahman ar-Rahim. So as we have discussed last time, we have two types of transmission. We have, as we said, the baseband transmission and broadband transmission. So for the baseband transmission, we said that the baseband is to transmit the digital signal, okay, as is using approximation. So the digital signal will be a digital signal like this, for example. So there will be a digital signal like this. And we want to send this digital signal as is using approximation. And one of the approximations is that we can use rough approximation where we have to use some kind of a sine wave to approximate this. So we can use some kind of a sine wave like this, okay, to kind of approximate the signal. And this is the baseband transmission. For broadband, and of course baseband transmission is useful if the channel has a low pass filter. Low pass filter meaning that the channel has a frequency spectrum that starts from 0 to a certain limit. And one example of this is what? LAN, bravo Ali. One example is the local area network, and we said that for local area network we use baseband transmission. We use this kind of approximation. Of course, this is a very rough approximation. A better approximation would be to use a more accurate signal like this. In that case, we require more than one sine wave as a composite signal to approximate the digital signal. And the more frequencies we have, the more accurate we can represent the signal. And we said that a digital signal of that type has an infinite frequency spectrum in general. So we have to use approximation because we do not have any physical medium that has unlimited bandwidth or infinite bandwidth. So in that case, we have to use some kind of approximation. We also talked about rough approximation, and we said that for rough approximation, the first example here, where we actually use sine wave, is what we call rough approximation. Why? Because it's the approximation level is very high, and what we're trying to do now is to approximate the digital signal using the least frequency, or the smallest bandwidth possible. Okay, so of course the frequency of this signal here is lower compared to this signal, because this signal is a composite signal and it's composed of multiple frequencies. So in that case, the bandwidth is higher. But here it's a rough approximation because this is the lowest bandwidth I can use to represent this digital signal. So to illustrate this idea more, is that when we have a digital signal like this, the original signal, so this signal can, for example, represent 1, 0, 1. Okay? So this is a type of a digital signal. But actually, if I have 1, 1, 1, in that case it will be a straight line, and I can represent that using a sine wave of frequency 0, which is a straight line, and in that case it's an exact representation of the digital signal. So, but the digital signal like this has different combinations. So I can have 0, 0, 0, I can have 1, 0, 0, I can have anything. Okay? And when we talk about rough approximation, we talk about the worst case. So what we say here is that we consider the worst case, and the worst case means that we consider the digital signal with the maximum type of changes, the maximum number of changes that we can have within this digital signal. For example, if we consider this digital signal, okay, and as we said, the different combinations could be 101, 100, and so on. What is the combination that gives me the maximum number of changes?
101 or 01?
Bravo, Ali. That's a perfect answer. So I have the maximum number of changes if I have 101 or 010. Why? Because for each 2 bits I have a change. So in that case I have to make lots of changes. And this is the rough approximation that corresponds to this. And this is in fact the frequency of the rough approximation that, or the bandwidth of the rough approximation that I can use. To illustrate this idea more, this example where we have a digital signal, okay, which can have 000 or 001 and so on. And we have the approximation, okay, using one sine wave with a different frequency. Okay, and we can notice here is that for this case the sine wave is frequency 0. Here we have a sine wave with frequency less than this, for example. So for this one, this is the highest frequency I can have because this corresponds to the maximum number of changes, similar to this one. So we will notice here is that for this one and this one, I have the maximum number of changes, and in that case, I have the sine wave with the maximum frequency. Any changes different from these will correspond to a sine wave with less frequency. Okay? So this is what we call rough approximation. So for that particular example, we use one single frequency to represent the signal. And we're trying to change that frequency to represent different combinations of the digital data that we have. Okay? Would be that we use multiple frequency components. In that case, we use a composite signal, okay, to represent the digital signal. So for that case, of course, I will end up with, so this is the rough approximation. In that case, we use only one single frequency. And as we can notice here, is that the frequency of that signal, okay, is n over 2. Why? Because assuming that I have 4 bits, not 3 bits. Okay? So in that case, I have here another 1. And in that case, I have a sine wave like this. Okay? So if I have 4 bits per second, assuming that I have 1 second and I have 4 bits per second, here I represented the 4 bits per second using a sine wave with frequency which is 2 cycles. I have only 2 cycles per second, right? So the frequency of that sine wave is actually, instead of 4, I use 2 cycles to represent that signal. So in that case, the frequency of that signal is n over 2. Okay? Because I use 2 sine wave cycles to represent 4 different digits or 4 different binary numbers. Okay? So for that particular case, the frequency is n over 2, and this is the sort of the minimum frequency that, or the minimum bandwidth that I can use to represent that digital signal, assuming that the digital signal has different combinations, and I'm using the worst case, which is the maximum number of changes. Okay. But as we said, this is a very rough approximation, right? So a better approximation would be to use 2 frequencies instead of 1. And in that case, we use a frequency which is n over 2 and another frequency which is 3n over 2. So we have here n over 2 and we have 3n over 2. So for that particular case, we use those 2 frequencies only. Okay? So in that case, as we can see, the this is a better approximation of the digital signal compared to this, which is clear, right? So this is getting closer to the digital signal. If we have 3 frequencies, we'll end up with something like this, which means that we have n over 2, 3n over 2, and 5n over 2. So in that case, the whole bandwidth is 5n over 2. Okay? So my bandwidth is 5n over 2. So if I represent the digital signal using 1 frequency, I end up with a bandwidth of n over 2. If I use 2 frequencies, I end with a bandwidth of 3n over 2. If I use 3 frequencies, then it's 5n over 2. So we have to answer 2 questions now. The first question is, why did I say that the bandwidth is the highest frequency even though I don't have zero frequency component here? We said that the bandwidth is the highest minus the lowest. So the lowest here is n over 2, and the highest is 5n over 2. So why we kept saying that if I use single frequency, the bandwidth is actually n over 2, even though I have only one frequency component at n over 2. So what happens is that, keep in mind that I'm representing a digital signal. This digital signal can take any form from 0, 0, 0, 0, all the way to 1, 1, 1, 1. If I represent this using a digital signal, 0, 0, 0, 0 would be a 0 frequency. So that's why I always have 0 frequency component, right? Because this digital signal can take any form, right? So 0, 0, 0, 0 is one of the possible waveforms that I can get, in which case I have frequency 0. So that's why I always have 0 component here. This is the baseband. For baseband, I always have 0 because it's low pass channel. So in that case, I have 0 component here, and the maximum frequency that I will have is when, if I have the maximum number of changes, and in that particular example, it's a 0101 or 1010. So this will give me the maximum frequency, which is n over 2. So that's why we kept saying that the bandwidth in that case will be n over 2. Why? Because I have lower components of frequency depending on the waveform that I receive, which depends on the combination of bits that I will get. Okay? Same thing. So if I represent the signal using 2 frequencies, then the highest frequency, the worst case, will be 3n over 2. And in that case, it's a 5n over 2. So that's the first question. The second question is, why do you think this one is a better approximation? This one is actually a better approximation than this one. And the main reason for that is this part here. The change between the lowest and the highest is very big compared to this. Here here the line is a little bit diagonal, but here it's very accurate. And this actually maximizes the accuracy when it comes to reception, because the change here is very, very high. So I can detect the difference between 0 and 1 easily. So that's why this is actually a better approximation. Okay, even though it doesn't look like it intuitively, but it's actually, in terms of reception, this is a better approximation. Okay, any question? So in baseband transmission, the required bandwidth is proportional to the bit rate. So if I have a specific bit rate, then, as we said, if we use one single frequency, rough approximation, then we end up with n over 2. If we use three different frequencies, then the bandwidth is 5n over 2. So it's always proportional to the bit rate. So if I want to increase the bit rate is the number of bits that I can send per second. So if I want to increase this, the bandwidth will increase proportionally. Okay? So as a simple table for mapping the bit rate to a specific bandwidth. So if I have a bit rate of 1 kilobits per second, if I use the rough approximation using one harmonic, okay, we call it harmonic, one single frequency. So in that case, the bandwidth is n over 2. If we use two harmonics, and in that case, the harmonics, they are called the ones, the first and the third. So when I say two harmonics, I mean the first and the third. Because there might be like a second harmonic which is not used in our particular example. Third harmonic meaning 3n over 2. So the first harmonic is n over 2. The third harmonic is 3n over 2. And the fifth harmonic, which is 5n over 2. So this is so if I use three harmonics, the first, third, and fifth, this will be the bandwidth required. And as you can see here, as I use more harmonics, instead of 500 hertz, the bandwidth is triple. Okay, and here the bandwidth is 5 times. Okay, but this one is more accurate, and the reception of using three harmonics will be much more accurate. Okay, so for the case of n equal 10 kilobits per second, so the half of this is 5 kilobits per second, and then this is the two harmonics and the three harmonics and so on. Okay. Type. What is so if this is a simple exercise. What is the required bandwidth of a low pass channel if we need to send 1 megabits per second by using baseband transmission? Well, I did not give you a piece of information here whether I use one harmonic, two harmonics, or three harmonics, right? So in that case, the solution goes through the three cases, okay? Because there was no given information about how many number of harmonics I use. So if I use this one is the minimum bandwidth using one single harmonic, and in that case it's simply n over 2. So if I have 1 megabits per second, the required bandwidth will be 500 kilohertz. Okay, and pay attention to the units, please. Many of you actually get confused with the units. So if I say bit rate, it's kilobits per second, but the bandwidth is in hertz. Okay. If I use two harmonics, then the bandwidth will be 3n over 2, and if I use three harmonics, it's 5n over 2. Very simple. So if I have a low pass channel with a bandwidth of 100 kilohertz, what is the maximum bit rate of this channel? Well, is there anything missing here? Similar to the previous example, I did not mention here whether I use one harmonic, two harmonics, or three harmonics. Is there anything missing here? No. The key word here is a maximum. And the maximum would be when? Now, this is the maximum bit rate. So here I fix the bandwidth. And I'm telling you what is the maximum bit rate that can fit in that bandwidth. So if I give you a digital signal with a specific bit rate, and I tell you what is the bandwidth, then depending on the number of harmonics, you can calculate it. But here it's the other way around. I'm giving you a fixed bandwidth, and I'm telling you what is the maximum bit rate that can fit in that bandwidth. Well, if you use assuming that there is no word maximum, okay, so let's try it exhaustively. So if we use three harmonics, so the bandwidth, which is in that case 100 kilohertz, equals to what? 5n over 2, right? So in that case, n equals 200 by 5 as kilobits per second. Right? So this is the case of 3 harmonics. So for the case of 2 harmonics, the 100 kilohertz equals to 3n over 2, which means that n is a 200 over 3. And for one single harmonic, n is equally 200 kilobits per second. So which one is the maximum? So if I use one harmonic, of course, which makes sense. Okay? So the maximum in that case would be if I use one single harmonic. Okay? Right. For broadband transmission, as we said, the bandwidth in that case, or the channel, would have a bandpass channel effect, which means that the bandpass is actually a special case of a low pass with no zero frequency component. Okay? So here, I don't have any zero frequency component. So anything after this is considered bandpass. Okay? So any low pass channel with no component in the zero frequency is considered bandpass. Okay? So in that case, the bandwidth is really the maximum frequency minus the minimum frequency. An example of this, as we mentioned before, is what? What? Bravo. Two examples are right. Wireless is one example. ADSL is another example. In both cases, we use bandpass or broadband transmission, because we cannot afford having zero frequency components for all signals. Because if we do that for ADSL, it's going to collide with our voice. If we do that with wireless, it's going to collide with many other signals that gets transmitted over the air. So we cannot use bandpass. We cannot use baseband transmission in that case. So in that case, what we need to do is to convert the digital signal into an analog signal with zero frequency component. So we have to convert the digital signal completely, not using approximation. We have to convert it to something else using a pure analog signal with no zero frequency component at all. Okay, so it's like we push the digital signal in the frequency spectrum away from the zero frequency component, and this can simply happen, like if we have a digital signal like this. So we can convert this to something like this. So in that case, I use an analog signal, and instead of using zero frequency component, or even if you have in that case something like this, even if you have 0, so in that case you will send an analog signal. You still send an analog signal with amplitude which does not change. So in that case, I don't have any zero frequency component, because I did not represent the digital signal using fixed frequency, zero frequency. Okay, so I have to convert the digital signal completely into analog without having any frequency component. An example. This is what we call amplitude modulation, or what we actually use for radio. We actually use that for radio and TV and even in wireless and so on. We convert the digital signal into an analog signal with with the same frequency but different amplitude of the analog signal. Okay. In other cases, we actually use the same amplitude but different frequency, and we have multiple ways to do that, which we will study in details in chapter 5. Okay. So in that case, as we can see, so we have converted the digital signal into an analog signal, okay, using the same frequency but different amplitude. When we send that through the bandpass channel, the bandpass channel has a bandpass filter that looks like this. So assuming that the frequency that we use lies here in the middle, okay, the signal will go almost as is, right? Because the frequency of this signal is within the frequency of the bandpass. So in that case, the signal will go through just fine. Assuming that this frequency is either is below F1 or higher than F2, in that case the signal will not reach. Okay? So here the signal goes through fine and it goes almost as is, assuming there is no noise, which we will talk about in a minute. So it will go almost as is, and in that case you will receive it, and then you convert this back. So because you have converted digital to analog, then you have to convert analog to digital. So you do the reverse operation. So it goes from here and it goes in a reverse path to detecting the digital signal. Okay? So this is how we use the broadband transmission. Of course, broadband transmission requires, in that case, to deal with higher frequencies, but not necessarily higher bandwidth. Okay? We have to push the frequency of the transmission away from the zero, but not necessarily to use higher bandwidth. And we will talk about that in more details in chapter 5. As we said before, as an example of this, what we call broadband transmission or modulation is what we use for ADSL. And as we said, for ADSL, we need to send a digital data over the telephone line, because the telephone line is originally used for voice transmission, okay? And voice is as an analog signal, has a bandwidth of 4K. So our voice starts from zero frequency, silent, to 4K. Okay? So this is the normal human voice. So we need to get away from the 0 to 4K frequencies. Okay? So we get the digital data and then we modulate it using what we call a carrier frequency. The carrier frequency is the frequency of the analog signal that we use. So we push the digital data in the frequency spectrum away from the baseband, from the 4K, which are used for voice. So in that case, we can send the digital data over the telephone line with no interference with the actual voice. And then we have to use a bandpass filter at the receiver. A bandpass filter, we can extract the digital or the analog signal with the higher frequency, and then we convert it back into a digital. So we can use that for ADSL without affecting the normal voice on the telephone line. So we use two converters in that case. We have to use digital to analog and then analog to digital. The device that does that is what we call a modem. A modem stands for modulation demodulation. So a modem is actually Modulation, demodulation. What it does is that first it modulates the signal, which means that it converts it to an analog signal with a carrier frequency that pushes the analog signal, the frequency of the signal away from the zero. And then at the receiver side, it does the reverse operation. It converts the analog signal back to a digital signal. This is what we call modulation, demodulation. And again, we'll discuss this in details in chapter 5. So until now, we are talking about a transmission, whether it's a baseband transmission or a broadband transmission, and we did not mention anything about the channel impairments. So until now, we assume that the channel is perfect, which is not practical. So in practice, we have different types of channel impairments that affects whether a digital signal or an analog signal. It affects all types of signals with different ways that we will discuss now. So we have three different categories of channel impairments. We have the attenuation, and we have distortion, and we have noise. The noise is nothing but a combination of attenuation and distortion, in addition to some other things. So so the general form of channel impairments is actually a noise. Noise can do all sorts of different things, as we will see. So for attenuation is very simple. Is the fact that the signal loses some of its energy, okay, in a form of decay of the amplitude, okay, but the shape of the signal is still preserved. So only the amplitudes, as you can see here, so from here to here, the shape of the signal stays the same, but the amplitude gets reduced. So what happens is that this represents higher energy, and from here to here, what happens is that the signal loses some of its energy. And as we know from the energy conservation law of Newton, that energy can neither be instantiated or destroyed, right? So this decay or this loss of energy has to go somewhere, and it goes in a form of a heat, and that's why sometimes when we hold a wire or something, we find it really hot, right? So this energy gets lost in a form of any other type of energy, such as heat or anything else. Okay. So this is what we call attenuation. To compensate for this attenuation, we in communication systems we use what we call amplifier. Okay, so if the signal is that's why, for example, when we talked in 455 about UTP and STP, we used to tell you that the maximum length of that UTP is what? Is 100 meters. So if you want to use a cable of more than 100 meters, then you have to use a repeater. Bravo عليك. A repeater or some kind of a modifier, or you have to regenerate the signal with higher amplitudes again. Because why? Because after 100 meters, the signal loses significant amount of energy that it cannot actually be received accurately after that. It becomes hard to receive the signal. So up to 100 meters, fine. But after that, the signal loses significant amount of energy. And this is the effect of a repeater. Okay? Or a hub or something like that. So what happens is that the signal gets amplified. Okay? So how do we measure the attenuation or the amplification? We measure that using the decibel. And some of you may have studied decibel before, and the decibel is simply when we calculate the ratio between the power here and the power here, and then we take the logarithmic to the base 10 and multiply that by 10, and we call this a decibel. So, for example, if the power here is if the power here is 1 watt, for example, is 10 watt, let's say, and the power here is 1 watt, this means that the signal lost significant amount of energy, and we want to calculate the attenuation here. So in that case, the attenuation is simply 10 in decibel. It's 10 log 10, 1 over 10. Okay? Which is how much? Huh? It's minus 10. This. Why? Because it's 1 over 10 is 10 minus 1, right? And 10 minus 1, it becomes the exponent goes out of the logarithm, right? So the minus goes here, it becomes minus 10. Log 10 to 10 is 1. So it becomes minus 10 decibel. And it makes sense. Attenuation is minus. Amplification is plus. Okay. So that's how we measure the attenuation. And the amplification, it's always, whether it's attenuation or amplification, it's always the power at the end divided by the power at the beginning, and then we take the logarithm to the base 10 and we multiply that by 10. So this is the decibel. So a quick example. So suppose that a signal travels through a transmission medium and its power is reduced to 1/2. The power is reduced to 1/2. So if it's if I have a line, here is P1, this one is a P2, and P2 is half P1. So in that case, the attenuation in decibel is 10 log to the base 10 P2 over P1, which is 0.5 P1 over P1, which is a logarithm to 0.5, which is log to the base 10 to 0.5 is around 0.3, and because it's less than 1, it becomes minus, right? So any logarithm less than 1 is minus. So so this means that a decay by half is always minus 3 decibel, which means the amplification or double, it becomes a 3 decibel. So attenuation by half is minus 3 decibel. Amplification by double is 3 decibel. 3 decibel is a very, very famous and common number. So because it indicates double or decay by half. Okay, so 3 decibel is either when it's positive, this means double the signal. If it's negative, this means that the signal has lost half of its energy. So a loss of 3 decibel in between braces minus 3 decibel is equivalent to decay of half the signal power. So another example, if a signal travels through an amplifier and its power is increased 10 times. So in that case, it's 10 log 10 to 10. And log 10 to 10 is 1, which means that it's 10 decibel. So multiplying the signal by 10 in terms of power is equivalent to a 10 decibel. Okay? So these are straightforward examples. Why people use decibel? Why don't we use ratio? What happens is that one reason for people to use decibel is that it actually converts the multiplication into a simple summation. Why? Because if I want to calculate the attenuation for this example, 0.1, 0.2, 0.3, 0.4, right? And here there is attenuation, here there is amplification, and so on. So I want to calculate the attenuation, amplification. I want to calculate the total effect of these particular stages. Okay? So I want to calculate basically the power here divided by the power here. Okay? But I don't have I have the power here and I have the power here. Okay? So in that case, I have to do what? I have to do P4 over P1. P4 over P1 is P4 over P3 multiplied by P3 over P2 multiplied by P2 over P1, right? So I have to do this, all these stages, because I have to do the effect of this and the effect of this. And if I take the logarithm of this, the multiplication becomes a addition, right? So we know that from math, right? So the logarithm of this multiplication becomes simple addition. So that's why we use decibel, because decibel is based on logarithmic, and logarithmic you can actually subtract and add the effect of each stage separately and very easily, right? So that's why people or engineers commonly use the decibel in that case. So for example, the effect of this line is simply minus 3 dB plus 7 minus 3 dB here. So the effect is 1 decibel. Okay? So the effect of this complicated line is that the signal has been amplified by 1 decibel. So in that case, I can get P4 over P1 very fast. So 10 log 10 P4 over P1 equal 1 decibel. So I can get the ratio very fast in that case, because I use simple addition to get the total effect of this line. So this corresponds to a transmission medium which caused the signal to lose half of its energy, and to compensate for that, I used an amplifier that multiplies the signal power, okay, with equivalent of 7 decibel, and then I used another transmission line which again causes the signal to lose half of its energy. So in that case, the amplifier compensated for these two stages and in fact added a little bit more energy to the signal. Okay? Any question? So sometimes the decibel is used to measure signal in milliwatts. So until now we use the decibel to measure a ratio between the power before and after the line, right? But sometimes people use, and less commonly actually, people use the decibel to even indicate the absolute power of a signal. And in that case they call it dBm. dBm, not decibel, in that case dBm, is to measure the power in milliwatts. And in that case, it's again 10 log 10 to the power in milliwatts. This power has to be in milliwatts. Okay? So in that case, it's dBm. So this minus 30 is minus 30 dBm, not dB. And remember that dB is a measure of a ratio. A measure of something that has no units. A ratio has no units. Right? A ratio of two values with the same unit has no unit. So when we divide P2 over P1, this is the ratio. It does not have a unit. Okay? So a decibel is measure of a something that does not have a unit. A dBm is the logarithm of something that has a unit. And in that case, the unit is milliwatts. Milliwatts. Okay? So, so if the power is minus 30 dBm, this means that minus 30 dBm equals to 10 log 10 to PM, which means that PM is minus 30 divided by 10, which is minus 3, and 10 to the power minus 3. 10 to the power minus 3 milliwatts. Okay? 10 to the power minus 3 milliwatts. Which in that case, 10 to the power minus 6 watts. Or 1 microwatt. Okay? So don't get confused about the units. So pay attention to that. Okay. So I can measure the again the attenuation as a rate, because we can divide any transmission line into stages. Each stage is 1 kilometer or 1 meter, right? So if I tell you that the attenuation is let's say like 1 decibel per kilometer. 1 decibel per kilometer. What is the attenuation for 100 kilometers? You simply need to add for each stage. For each stage you have 1 decibel, right? So for 100 you have a 100 decibel. So you simply multiply 100 times the rate. So here the loss in a cable is usually defined in decibel per kilometer. So if a signal at the beginning of a cable with minus 0.3 decibel per kilometer has a power of 2 milliwatts. Okay? So what is the power of the signal after 5 kilometers? Well, simply it's minus 3 per 1 kilometer, and I have 5 kilometers, which means that I have an attenuation of minus 1.5 kilometers for the entire cable, right? And minus 1.5 is equal to 10 to the power, 10 multiplied by the logarithm to the base 10, P2 over P1. And what I have is actually P1. I can get P2 easily, right? So, so P1 in that case is the power at the beginning of the cable, which is P1. So 2 milliwatts, or 2 times 10 to the power minus 3. So P2 divided by P1, I have P1. So I can simply, I can do that easily, even though minus 1.5 equals to 10 logarithm 10 to P2 divided by 2 milliwatts. Okay, so this corresponds to so minus 0.15 equals to logarithm 10 P over 2. So this means that P2 equals to, so when I get the log to the other side, I convert it into a 10 to the power something, right? So this means that P2 equals to 2 times 10 to the power minus 3, 10 to the power. So this is P2. In what? In watts. Okay? So you can get 10 to the power minus 0.15 using the calculator, and it becomes, all of them becomes a 1.4. Okay. Okay, so this is attenuation. So attenuation, as we said, it does not change the shape of the signal, rather it changes the amplitude of the signal, or in other words, it actually causes some decay in the energy to the signal. Okay. Distortion, on the other side, is different. Distortion happens to composite signals. And when we say composite signals, we have discussed composite signals before, and we said that composite signal is composed of multiple frequencies, right? It's composed of more than one frequency. And what happens is that distortion causes different delays or different shift in the signal for different components of the frequency. In other words, this signal is composed of 3 different frequencies. So what happens is that distortion causes the different frequency component to have different delays. For example, this frequency component has no delay or no phase difference, right? So this is before the distortion, this is after the distortion at the receiver side. This signal, for example, as you can see, it was shifted this way, right? A little bit. So this signal, for example, has been shifted this way, a little bit. So it causes different frequency components to have different phases. Okay? The result is that if you get these 3 frequency components at the receiver and then you reconstruct the signal, it becomes like this. And as you can see, this signal is a deformation of that signal. So the signal has lost its original shape. Not only the amplitude in that case, but the shape. The shape itself has been changed. Slightly changed. Okay? So this is the distortion. So the distortion does not necessarily cause the signal to lose energy, but it causes different phase shifts to different frequency components of the signal. Okay? So this is what we call distortion. So we cannot easily measure the distortion the same way we did for attenuation, unfortunately. Well, of course, there are some ways to measure that, but it's very complicated and it's not discussed as part of this course. So what we need to discuss next is the noise. And the noise is, it causes attenuation, it causes distortion, and it causes even frequency changes of the signal. Okay? So noise in general is a combination of attenuation and distortion in addition to some other effects, such as not only causes the frequency components to have a different phase shift, but even the frequency of the signal gets changed. Okay? And to talk about frequency, we can classify, to talk about noise, we can classify noise into 4 different categories that are discussed here, although especially in wireless there are tons of other noise types which we will not discuss, but the 4 common noises here are classified based on the source that caused this noise. For example, the thermal noise, if we talk about a wire, a normal wire, when the signal travels through a wire, there is an internal noise that happens to the signal, okay, inside the wire, without any external effect. So if you take any object, okay, and then you get a signal from the beginning of this object to the end, the object will have, without considering any external effect, the object itself will cause some noise. This is the noise that we call a thermal noise, and it's the cause of that thermal noise is the actual electrons inside that wire. So this wire, when the signal travels through the wire, okay. So a wire, and the signal comes here. Inside the wire there are some electrons, right? And these electrons, they move in a random fashion. Okay? So this random movements of the electrons causes the signal to have some kind of noise. So instead of having the original signal, you have some deformed signal like this. And this is what we call a thermal noise. So again, a thermal noise is caused by the internal electrons of the wire, okay, not considering any external source, and it causes some deformation to the original signal. So this is the thermal noise. The second type of noise is what we call induced noise. Induced noise is coming from an external source. So all the three other types of noise here, whether it's induced noise, crosstalk, or impulse noise, these are caused by external sources. Depending on what type of sources that cause this signal, that cause this noise, we have different names. So for example, induced noise is caused by like motors or anything outside of the wire, okay, which has like some vibrations, or maybe like microwave at home or something like that. These type of devices, these are external from the wire, yet they cause some noise on the signal that goes inside the wire. Why? Because the vibrations or the activity that happens in that external device, they sometimes emit some energy, okay, and the wire acts as a receiving antenna to this energy. So it receives even some very tiny little part of that energy. And this tiny little part causes again some deformation to the signal that travels through the wire. Of course, when we talk about wireless, this becomes more eminent, right? More evident, because the signal travels through the air. If you have a motor or anything that vibrates, or a microwave or something like that, it actually causes some energy to emit from that device to the air, and that causes the noise to the signal. So in that case, the receiving antenna on the other side receives small part of that energy. Even when we talk about wire, even though for wire the effect is very small, but it's there, the wire actually acts as a receiving antenna to tiny little part of that energy, which causes the noise to happen. Okay? And that's why we have taught you before in 455, for UTP you have to have You have to have different levels of isolation. One, to protect the wire from inside, not to emit the energy outside, and another isolation outside to minimize the effect of external sources of noise on the wire inside. So one to protect the energy from inside, and the other one from outside, right? So that's why we needed to have different ways of isolating the wires inside the cable. So induced noise is caused by external sources such as motors or other devices. Crosstalk is caused by another wire. Okay, so crosstalk is caused by another wire. So another wire has a signal that goes in a specific direction, in any direction, and there is another wire next to it, close to it. An example of this is what, again, UTP. For UTP or STP, you have the multiple wires, right? So crosstalk talks about the fact that one of these wires, again, loses some of its energy, which we said before. It gets lost in a form of a heat, or it gets lost in a form of any kind of energy that goes and affects the signal that goes in the other wire, and the other way around. So any two wires, they cause some energy to each other. They cause some noise to each other. Sorry. They cause some noise to each other. Right? So the crosstalk happens by another wire that causes this energy, this noise to happen. And one of the ways to overcome this is also what we taught you for 455. To get rid of the crosstalk is to do what? Twist. Bravo. I don't expect that this to be answered. Bravo عليك. This is a very good answer. When we twist, we don't actually eliminate the crosstalk. We don't eliminate it. Remember that. We don't actually eliminate the crosstalk. What happens is that we kind of make the effect of crosstalk homogeneous across the whole line. Because what happens is that if you have one line here and one line here, okay, we don't want the effect to be on the upper side of the wire. When we twist it, we make the effect homogeneous across the entire wire. So we make the effect from up similar to the effect from down. So we kind of homogenize the effect of crosstalk across. And of course, by having some isolation, we try to minimize that effect. So twist and isolation together will minimize the effect of crosstalk. The last type of noise is what we call impulse noise. Impulse noise is actually caused by like an earthquake or a very big event that happens in a very short period of time. And this usually causes impulse, like huge amount of noise at a very short period of time, but it goes away after that. And again, each of these type of noises, it has some ways to mitigate. So for example, impulse noise has different ways to mitigate this noise, different from crosstalk, as we said, by twisting, different from thermal noise, different from these type of things. Thermal noise, usually you cannot get rid of, because this is something internal. You can sort of minimize it using proper manufacturing of the material. But other than that, you cannot do anything. But for induced noise, for crosstalk and these things, you can use different techniques to mitigate. Okay? So, so this is the way that we measure the noise effect is by, again, the ratio between the actual power of the signal divided by the noise power. So we have the power of the signal, we divide that by the noise power, and we take the decibel of this. This is what we call signal to noise ratio. So this example here talks about two signals. The original signal in that case is very high. It has a high level of power, and the noise power is low. So this is the signal and this is the noise. So when you add this noise to the signal, it becomes something like this. And as you can see, this is the signal plus noise, which has high signal to noise ratio. High signal to noise ratio is good. High signal to noise ratio, it means that the effect of noise is minimal. Right? Because high signal of noise ratio means that the power is much higher compared to the energy. So this is good. So if you have low signal to noise ratio, this is bad, because this means that the noise power is comparable, or it's close to the original energy of the signal, which means that you end up with something like this. So if the signal itself has low power, which is more or less similar to the power of the noise, you end up with something like this. And as you can see, you can hardly distinguish this signal from the original signal. So the signal is totally deformed and you cannot actually extract anything out of it. Compared to this signal where although the shape of the signal has changed, but I can still detect these sharp edges and be able to detect the signal, the original signal from this noisy signal. Okay? So just to go through this example quickly, if I have the power of the signal of 10 milliwatts and the power of the noise is 1 microwatt. So what is the signal to noise ratio? It's 10 milliwatts divided by 1 microwatt, and then I take the logarithm of this and multiply it by 10. When I do that, remember the ratio and remember the units. So here it's 10 milliwatts, so this is actually 1000 milliwatts. So 1 microwatt is 10 to the power minus 3 milliwatts. So you divide the ratio, you divide the values using the same units. You divide the values using the same units. So either you divide that by 1000 or you multiply that by 1000 so that you can divide these values over each other. So in that case, there is a simple mistake here that this is actually micro. Because this is microwatt and this is milliwatt here. There is a typo here. This is actually microwatt. So 10 multiplied by 1000 is 10,000 microwatt divided by 1 microwatt, which is 10,000. And then to take the logarithm of this, it becomes 40. So the signal to noise ratio here is 40 decibel. Okay? So the value of the signal to noise ratio for a noiseless channel is simply infinity. Why? Because a noiseless means that the noise power is 0. To divide by 0 is infinity. A logarithm of infinity is infinity. Right? So the signal to noise ratio of the noiseless channel is infinity. Okay? So we'll stop at this point and